Hello, everyone. I'm Avraam Tolmidis. My career has focused on leading engineering teams to build robust systems, from my PhD in machine learning to my professional experience across autonomous systems and fintech. Today, we are discussing the shift required of every engineer, moving from building systems that merely work to building systems that work and explain how they work. This is the mandate of explainability. This talk is structured around the principles and tools we apply in high-stakes ML systems to achieve transparency and accountability. We will discuss why explainability is crucial in systems where decisions impact human lives and require accountability. Applying clear principles helps engineers build ML systems that are interpretable and trustworthy. And we will use specialized tools and best practices in order to support the creation of accountable and transparent machine learning models. The simple reality is that we don't know why is not an acceptable answer when decisions impact human lives or finance. In healthcare, for example, explanations are needed for diagnostics. In autonomous systems, they are needed for safety audits. Explainability is essential for trust, fairness, and regulatory compliance. Before we dive into engineering best practices, let's establish the fundamental tools we use to break open the black box. Explainability is the difference between a black box that predicts and a glass box that predicts and justifies. Our goal is to use tools to make models transparent, supporting auditability and trust. The explainable AI landscape is broad, covering intrinsic methods, inherently transparent models like linear models or decision trees, and model-specific methods like saliency maps, attention mechanisms in neural networks, and so on. We focus on model-agnostic tools, SHAP and LIME, because they solve the critical engineering problem of standardization across diverse models. Thus, they are best fit for scaling explainable AI across different models and industries. If the explainable AI universe is so large, why do we focus on SHAP and LIME? Well, because they are the two essential tools needed to solve the full scope of the engineering problem. Referencing to the previous slide, on the broad explainable AI landscape, SHAP satisfies the audit and compliance need. It's the most mathematically rigorous and provides a globally consistent contribution that is required by legal and regulatory teams. What is the SHAP use case? Auditing, compliance, consistency. This is non-negotiable for high-stakes industries. LIME, on the other hand, satisfies the debugging and UX need. It supports fast prototyping and real-time failure analysis because it's quick and provides human-readable output which developers and product managers rely on daily. What is the LIME use case? As mentioned, debugging, UX feedback, and when we need speed, some local insight. It's necessary for the development lifecycle. They're the perfect pair. SHAP gives us the truth for the regulator, and LIME gives us the rapid insight for the developer. So, SHAP means regulator and audit, LIME, then we think of developer and speed. We start with SHAP, which is the gold standard for auditing. It's rooted in game theory and provides a precise, quantitative breakdown of feature contributions across all feature combinations. This consistency makes it globally consistent and the ideal tool for regulatory compliance. It is worth noting, though, that while powerful, SHAP is computationally intensive, and this can be an issue in real time or large scale application scenarios. The rigor of SHAP comes from finding the average marginal contribution of a feature across all possible coalitions of other features. The formula looks complex, but the core idea is simple. We measure how much a feature I changes the prediction when it joins every possible existing group, and then we take the weighted average. Let's make the theory concrete. We are predicting loan approval. Our baseline, the average approval rate, is, let's say, 60%. We only care about two features at this point, age and credit score. Our goal is to calculate the fair contribution or the SHAP value of age to the final prediction. We do this by measuring age's impact in every possible order. We have two calculation steps, or two orders. Order one is age first. We measure the contribution of age when it's added to an empty set. That is, a prediction with age minus the baseline. In order two, age last. We measure the contribution of age when it's added to the set that already contains the credit score. This is the prediction with both features minus the prediction with just the credit score. We sum these two contributions and apply the weight. If age reliably pushes the score up in both scenarios, regardless of the credit score's presence, its final SHAP value will be strongly positive. This calculation is mathematically guaranteed to be fair, and it's the heart of SHAP's auditability. LIME, conversely, is our primary debugging and UX tool. It is model agnostic. It works on any black box. LIME sacrifices global consistency for local fidelity and speed. It generates a simple local surrogate model to mimic the complex model's behavior right around the prediction point. This is fast and delivers the human-readable explanation needed by developers and product teams. LIME achieves its speed by minimizing this loss function that we can see on the slide. It balances two things. Local fidelity, making sure that the simple model G matches the complex model F closely near X, and simplicity, which is the omega of G, ensuring the explanation is easy to understand. So LIME balances being accurate locally and being simple to be understood. So let's apply LIME to a borderline rejected loan application X. Remember, LIME doesn't look at the whole model. It just focuses on this one prediction. For context, our target prediction is borderline rejected. We need to know why the model did that. First, we have the perturbation step, step one. LIME creates hundreds of slightly modified versions of application X, some with higher income, some with lower debt, and these are the samples that we will use. Step two, we have the surrogate fit. So after using the perturbation with LIME to fill out the local decision boundary, we use the surrogate fit, which covers the steps 2 to 4. And in these steps, during these steps, LIME asks the complex model for predictions on all those modified samples. It then assigns a high weight to the samples that are very similar to X and fits a sample linear model to only the high weight area. So for surrogate fit, we can keep two things. One, high weight is given to closed samples, local fidelity, and two, a simple linear model is used, simplicity. Then we have the third part of our algorithm, which is the result, step 5. So this simple linear model that we use reveals, for example, in this case, rejection was primarily due to high debt to income ratio, for example, and low savings. This explanation is generated in milliseconds. So in the result phase, the linear equation provides the feature weights. The key advantage is that we get fast insight into the specific features that are causing the localized decision. This rapid local explanation is LIME's core advantage. It allows developers to immediately debug the borderline behavior or give a precise feedback to the applicant. So, if we want some final takeaway on LIME, we can say that LIME is fast enough for real-time debugging and UX. The key is understanding when to use each. SHAP provides the rigorous, consistent feature accountability needed for local audits. LIME provides the fast, qualitative insight needed for debugging and quick user feedback. Now, let's look at the lessons learned when implementing these tools in production environment. From my work on risk assessment platforms, the lesson is feature attribution is a core product requirement. We don't just deliver a score. We have to provide the top X features, 5, 10, however many needed, that drive that score. Engineers must design the explanation into the API layer from day one. And looking at the work I did in autonomous system, one thing I learned is the following. Explainability must be causal and real time. Overall, in the automotive industry, traceability is extremely important. You want to understand the behavior of the vehicle and debug things. You might have an audit, and definitely there must be full traceability when you have an investigation of an incident. So we need logs that show, for example, that the vehicle braked because the radar confidence dropped below X%. This requires real-time feature confidence monitoring as a core safety feature. The biggest obstacle is often the cross-functional mandate. Engineers must design different explanations to satisfy legal, policy, and UX, who all require different levels of detail. This requires stakeholder alignment from the design phase. So, how do we engineer for this? Well, it starts with governance and automation. First, design and governance. Define the required explanation depth before training. Then, establish feature governance via our feature store to guarantee the auditability and reproducibility of every feature definition. Finally, automate it. Bake explainability into CI/CD. Pipelines must automatically generate and store SHAP artifacts. Crucially, they should test for explanation drift. If the feature importance suddenly shifts, the pipeline must fail to prevent silent, dangerous model changes. Let's bring this all together with a demo looking at 4 distinct scenarios in credit risk assessment. Since it was a bit more challenging to have the demo live, I will give the results on the following slides. So the demo uses a random forest classifier on the German credit data, 48 encoded features. Our prediction goal is class 1, which is rejected. We will compare SHAP's consistency against LIME's local insight. Our first case is, as I mentioned, the auditable rejection. This applicant was clearly rejected with a high probability, around 0.89. And our goal is to provide the precise feature counting to justify that decision. We'll use a plot for this. The plot starts at the expected value, the average risk across the whole dataset, and then features are added one by one, cascading down the prediction. Red bars push the risk higher towards rejection, and blue bars push the risk lower. The final output, the sum of the baseline and all feature contributions, is the model's final high rejection score. So the end of the waterfall represents the final prediction score. This is the auditable rejection. The plot shows that critical credit history and no checking account, as well as the feature that the dataset encodes as purpose A45, drove the 0.89 rejection probability. These are the longest ones of the red bars, as you can see here on the plot. So this is the precise feature counting required for compliance. As you look at the plot, the large dominant red bars are the reason for the rejection. As we mentioned, these are high-risk features like the credit history and checking account status. And these risk factors overwhelm any smaller mitigating factors, which are represented in the blue bars, that might be present in the application. Note that the blue forces are present, but they're too small to change the outcome. So for the engineering team, this plot provides the quantifiable evidence required for compliance. It shows exactly why the decision was made, making the model's action fully auditable and defensible. So SHAP, as you see in this case, delivers the quantifiable evidence needed to make the rejection auditable and defensible to regulatory bodies. We will switch now to SHAP case 2, the auditable approval. We've seen how SHAP justifies a rejection. Now we'll see how it justifies an approval. We see in this image a waterfall. This is flow energy cascading from a high point to a low point. And our visualization of the flow is the prediction probability. It starts at a high point, the average risk, and features a cascade down, pushing the prediction higher or lower until it hits the final decision. So the features will cause the probability to rise, red, or fall, blue, until we reach the final approved result. Let's look at the actual plot now. So this is the force plot visual of the data. It's an interactive way to visualize the flow of the prediction. The prediction begins at the base value, the average risk, and it's pushed left by blue forces and right by red forces, leading on the final low rejection risk. So, as you can see, the prediction is strongly pushed to the left towards approval. The large dominant blue forces like credit amount, a small, or age, a favorable, clearly outweigh the small red risks. This demonstrates the symmetry of auditability. We can prove this visual evidence to a regulator, providing the approval was justified because the quantifiable stable features were sufficient to overcome any residual risk. We now switch to LIME, the debugger's tool to examine local decisions. This is case 3, borderline rejection. We are looking at an applicant whose prediction probability was right around 50%, a true coin flip. LIME generates a local plot by creating thousands of similar synthetic data points, seeing how the black box responds, and fitting a simple linear model to that local area. This gives us local fidelity immediately. The resulting plot shows the conflicting local factors causing the close call. You see one specific positive factor, like checking account status, for example, which has a small balance, pushing for approval, nearly perfectly balanced by a high risk factor like credit history, critical account, pushing for rejection. These two specific features are fighting for control of the outcome in this local area. This is instant insight for debugging the decision boundary. If we didn't have LIME, we wouldn't know which features were causing the model to be so undecided. So LIME quickly reveals which specific features are causing indecision, guiding feature engineering or data collection efforts. Our final and perhaps most critical case is failure analysis. This is a false negative. The applicant defaulted, but our model incorrectly predicted approval. We need to know what tricked the model. LIME is essential here. It doesn't care that the decision was wrong. It just explains why the model thought it was right. This involves mapping the local features that incorrectly weighted the decision towards approval. The plot shows strong blue bars dominating, driven by factors like long loan duration or favorable housing. These are features that misled the model in this specific region of the data space. This insight is invaluable for the debug loop. We learned that the model learned a misleading local pattern from these specific feature values. We can now precisely target our data scientists to inject more failure examples with this specific characteristics, accelerating our path to a trustworthy system. So LIME provides the precise localization needed for failure analysis, allowing for efficient targeted retraining and correction. To conclude, the journey from black box to glass box is complex, but the required engineering principles are clear. Explainability is very important in high stakes environments, so all the above is very critical. We can choose SHAP or LIME based on the use case we have. SHAP for consistency and audits, LIME for local debugging and explanations on a local area. And we need to integrate explainable AI to all our CI/CD pipelines, so we have transparency across our model lifecycle. And also, last but not least, we need to design the explanations through aligning with stakeholders early in advance, and this will boost trust, accountability, and system effectiveness. Thank you very much for your attention. I'm happy to answer to any questions